our last session, Alistair Walker, coming all the way from Cerro Tololo in Chile, is going to give us a talk.
Okay, so as is traditional in these talks, you spend the first minutes talking about this gentleman here, who I've only met for the first time today, unlike most of you. And I thought the only thing that we had in common before this was that both our first papers that we wrote to journals were on lunar occultations, spaced 20 years apart. But however, at morning tea this morning, George told me another one, and the other thing we have in common is my wife. So I pricked up my ears to. No, I'm talking now. There's this one. And so you can interrogate him about this story. However, I also find out that many Carnegie visitors and staff and everything also visited my wife. And that's because she's a doctor in La Serena and has been putting people right for many years, including George. So I hear. So anyway, let me get on with the astronomy because I've only got 15 minutes. And I'm talking about Antlia 2. And there's the team. The paper was published earlier this year. So you can go and read it if you want. You know all about this stuff. The Milky Way halo is not only the smooth part, which is interesting enough in itself, but it's full of all sorts of stuff. Satellite galaxies, stellar streams, globular cluster, and also dark matter, which hasn't been mentioned today. But Aura stars are a crucial tracer population. And in this paper, we're using Aura stars to tell us about Antlia 2. Oops, press the right button. Pointing out that satellite galaxies of the Milky Way has kind of been, they're everywhere, ranked in the last few years due to the big surveys taking place on bigger and bigger telescopes, whereas the last big increases, the dark energy survey on DECAM and Pan-STARRS and various others. So let me go on. On the sky, Antlia is one of these completely tiny constellations in the south that were originally mapped by Abbe de la Caille. And this is a really interesting book by N. Glass, who I used to work with many years ago. And if I can press my button, ooh, that was not the one I wanted to press, this one. Antlia 2 fills this corner of the constellation. And so, and indeed, if it was 1,000 times brighter than it really is, that's what it would look like. I found this on Wikipedia, actually, which was interesting. And
the bright artificial blob that you're talking about?
This thing.
What thing?
That is what Antlia 2 would look like if it was 1,000 times brighter. There's a large magnetic cloud.
So what's its latitude?
Oh, it's minus 30
If it was 1,000
times brighter. That's what it would look like. It's not, though. It's 1,000 times fainter than that simulation. Okay, and you can't see it, and you can't find it virtually at all because it's at low galactic latitude, about 15 degrees, and it's very low surface brightness. So this is a very useful diagram, which is logarithmic in both axes. So there's the absolute magnitude that way, and there's the half-life radius this way on the sky, and all these things are Andromeda and Milky Way dwarf galaxies. And you can see that the dotted line is the surface brightness limit. And so Antlia 2, along with a very similar, it looks like Andromeda 19 that I really don't know much about, and Crater 2 is the other one we've worked on, are really pushing down to very low surface brightnesses. So Antlia 2 was discovered by a cluster of variable stars from Gaia that were originally interpreted, I'll get onto this in just a second, originally interpreted as being Aura, but in fact turned out to be the anomalous Cepheids. So the distance was a little different. This just shows, I haven't got time to explain this, but this is a diagram that shows which dwarf galaxies are likely to be stable and which ones are likely to be unstable against disruption in the field of the Milky Way. And below the line are things that are basically expected to be disrupting. And so it's things like Sagittarius, Crater 2, Antlia 2, and so on. So
The density is lower than something become unstable against disruption.
Yes.
Okay.
So we observed with DECAM, which looks not like that, but is effectively, that's what it is. It's a giant camera. There have been basically 3 papers on this object. The discovery paper, Torrealba, a spectroscopy of RGB stars from G et al. Looking at radial velocities, and our paper, which was led by Kathy Vivas. And this was my part, which was doing all the photometry, so I'll jump over that and show you the results. And let me go to this one, which is more interesting. Now, there is enormous numbers of stars there, which are almost all galaxy stars in front of us. And this is, there's probably, well, I said there was 1 million stars on the full field, and there's probably 250,000 galaxies that have been thrown out and not shown on any of these plots as well. And so the photometry is interesting to do, but you can do it. The observations were done in almost full moon, so that we used R and I, which are not, you know, what you'd choose if you had darker time only. And you can see that there's lots of variable stars. And there's the Araliras. There's bright Araliras foreground. The greens are anomalous Cephids. And there's interestingly enough, there's a couple of faint Araliras, if you can see the sort of orangey things, a bit hard to see down there. And here's the stars that are meant to be radial velocity members is from G Thalia.
What distinguishes the faint RLRs? Is it just because they're low in this diagram?
Yes.
Okay.
There's 2 of them. You don't really expect them to be there if they're part of. Yeah, and this is what light curves look like, and there's a whole range of things here. But you can see that all the light curves over the whole range are well sampled, and you can see there's the nasty things like, you know, RRDs and so on and so forth, Blaschko's, but everything's pretty well sampled. On, and here's the distribution on the sky. I didn't mention we observed in 4 fields, so the DECAM field is quasi-circular with 61 working CCDs of 62, so that's the gap at the bottom. And you can see the sort of elliptical, which was also demonstrated from the RGB stars that were identified in other studies. And the faint Araliras are sort of, well, yes, they're just off to the right there.
Did you say bright? Those are foreground somehow?
Yes, they're foreground. Yeah.
And you think the faint the background?
Oh, well, I'll come back to that. Yeah, there's no good explanation for them is the I think the reasonable solution. Okay, these are the stars that you can measure on Gaia, the proper motions, which doesn't include the Araliras, but includes the spectroscopic members, which you can see are all there. The bright Araliras are all over the place, so that's consistent with them being all foreground. And the anomalous Cephids are consistent with being anomalous Cephids in Antler 2. The Bailey diagram looks like this, which is typical for dwarf galaxies, where you've got a spread. This is a sort of, you know, the Osterhoff 1.5 type population. Now, this is a nasty piece of the sky to do the work in, because you're getting close to the galactic plane. We worked down the extinctions in the usual way from Schlafly and Fichtbeiner, and then calculated distances from the I-band PLZ relation of Caceres and Catalan, which is, again, a usual way of doing this. Remember, we've only got 2 bands, so we cannot measure all of distance using the PLZ relation without, and reddening, without assuming a Z, You can't, there's too many variables. You need 3 colors to do that, or even 4. So we assume the spectroscopic RGB mean metallicity and its dispersion in doing this. For the RLIs, we assume that's the same as the RGB stars, which is reasonable. So this is elliptical on the sky, but the distance, there's a distance gradient, and this is interesting. The distance gradient is actually real. It's not just an artifact of the reddening. And indeed, and you can see that these plots show all of the RLI show the distance gradient, and then we can take the ones that have got the lowest reddening that we measure, and you see exactly the same thing. And the way the reddening goes in this coordinate system, we've actually rotated the coordinate system slightly. So we're going along the sort of the major axis of the distribution.
What's the upper right hand there?
It's the run of the reddening in the position and spatially in the sky. And you can see it's very different from the run in the distance. And the bottom right, and I'll get to a minute talking about the model, shows what a model prediction is, but let me just pass over that for a moment, just say that only that. And so what it turns out is that this is kind of like the Small Magellanic Cloud, in that you can see there's a distribution in the sky, but there's a huge dispersion in the distance. So it's elliptical, as it were, in distance, far more than it is on the space of the sky. So this thing, it's 20 kiloparsecs, right? And so this is an enormously large object, and it's invisible because there are not that many stars, and they're all over 10 gig years old. Remember, you saw this color magnitude diagram. Basically had nothing but the RLIs. You can argue a little bit about their anomalous Cepheids, and you say their production of binary coalescence, right? And yeah, but we can't absolutely rule out that there are, and blue stragglers are their progenitors. The color magnitude diagram showed some blue stars, but all the bright ones, which are bright enough for Gaia, are white dwarfs very close to us. So it's likely that there is no intermediate age population at all in this galaxy. I should have said that earlier. Okay, well, we've got a model that's calculated by Dennis Erkal, and I'm not sure this is the best way to look at the system, but what the model predicts is that, and the RLIs are plotted on the right. Now, the agreement, the dispersion in, let's say, the horizontal, this is looking down on the orbit. The dispersion in the, let's say, horizontal direction between the model and what the RLI distribution is actually agrees quite well. The model would say that we're missing actually quite a lot of the RLIs if they follow the distribution of the model points. And that's just because we didn't observe the whole thing. It also predicts that there are long tidal tails, and the interesting thing would be to see if there are RLIs along that. Now, that would be an enormous project, and probably one that's best done by waiting for Rubin to do. Doing, more decam 3 square degrees around the main body, let's say, would be a possible project.
Alistair, is the origin of this plot the galactic center or the sun?
No, the object. That's an interesting question. North. No, I don't think it can't be the galactic center. I mean, the orbit is calculated by Yet Alia, is basically the object is very nearly in the outer part of its orbit at the moment. It's 125 kiloparsecs out, and the orbit runs from 130 into about 30. So it's way out.
So it's tilted by a large angle.
Yes.
Yeah, so and we're looking down on the plane.
Yes.
doesn't really matter.
Doesn't really matter too much at this size. Yeah, I'm not sure of that. I'll have to look that up. Yeah. Okay. Well, that's about it. So what we know, Antlia 2 is large. It's almost certainly disrupting. So whether it's going to survive, you know, in another 1.2 billion years when it's meant to get within 30 kiloparsecs of the galactic center, will be probably its last. It's old. RLIRAs are very prominent. The small population of anomalous Cepheids, which are consistent in number with just being coalescing binaries and not intermediate age stars. And as I said, it's disrupting. The model actually says that it was very severely molested during its last perigalactic passage 800 million years ago. That's when it really distributed the RLIRAs. But the model, the long tidal tails, the model says came out in the previous time it went around, which was 3 billion years before that. How true that is, I'm not sure. So as I said before, Ruben will help us with finding RLIRAs in the tails. Detailed star formation history is probably possible. I mean, you know, we were observing almost at full moon on all this observations. This was kind of, you know, DD time that was available after it was discovered. So one could do a lot better, I think, in the color magnitude department. And it could indeed be cleaned up again with Ruben proportions.
Doesn't tell you anything.
This
Really.
is faint, remember, so you can't do it with Gaia.
That's why I provide these other views.
So that's it. Thank you.
Well, if you
Is there
said
any questions?
25% over the entire heat shield,
What am I supposed to do with this? Talking to it. Okay. Well, can you speculate what were the two antecedents of this collision? What were they?
What do you mean by
Well, this is a collision, huh? Between a tidal interaction between two galaxies.
Yes,
Well, what kind of galaxies were they? They're all old.
they're all
So-
old. Yes, they're all
So
old.
what kind of galaxies
Oh,
were they?
this, whoops.
You speculate. Yeah, they must be a rare, very rare event.
Well,
It's the Milky Way.
yeah.
This is an interaction between the Milky Way and that and a
Yes,
galaxy.
and this galaxy,
Oh,
this little thing.
And it's not at very center, George. It's gone back out.
It's gone back out. At pericenter, it's in at 30 kiloparsecs.
Oh, okay. Thank you very much. Thank you very much.
Just to add to that point about it not being at pericenter, I wonder whether it'd be worth searching for the tidal tails in blue horizontal branch stars in existing data.
Yes, we have not done that.
Yeah, but it
Yeah.
might just be there, you know.
Yeah.
Hi, thanks. I have a question about the distribution of anomalous Cepheids versus RLIRA. It looks like they're offset a little bit, and I wonder if this is just because of reddening or if there are some physical reasons why they would not have the same kind of photometric center.
So I don't think it's reddening. I mean, they're very bright. We would have detected like, all of them for sure. Physically, I cannot answer.
Okay.
How inclined is the plane of this orbit to the plane of the galaxy? Because if they're very similar, then it's going to be hard to find the tidal tails.
I can't remember the number, but it's large.
Okay.
Very large.
I have a couple more questions, and you still have some time, Alistair, so you're not off the hot seat yet.
And so what about those two faint RLIRA stars? Are they found at a similar place on the
Yes.
sky?
So you say, okay, it's two. If there'd been one, then you can say, oh, this is consistent with this being part of the galactic distribution. Two is too many at the distance that they're at. They're at something like 150 kiloparsecs. Right. So, but you say it's only two, So there is a statistical chance that, yes, this is,
Yeah, but Alistair, the field is really big.
yes, it's 3 square degrees. It's just before the 12.
Two might be okay.
2 might be okay, yes, but yeah,
Are they near the center of the event
they're yes, they are kind of behind the body. But you see, I'm saying, if you believe the model, then there is not meant to be a tidal tail or anything from Antler 2 out at further distance there. Now, maybe the model's wrong or whatever, or it's something else, another stream.
Yeah, really interesting. Those distant RLR stars are cool. All right, let's thank Alistair one more time.
All this back again.